Hey everyone, so we're going to be going over vectors a little more now. Maybe you have watched the video of Mr. Fairbank kind of going over vectors, talking about tail method. Maybe you're doing this first, depending on kind of how we're doing it this time. And so what I want to go over really first is just what a vector is, how are we kind of using some of this. And so to do that, you will hopefully need, 5 colors. I use 6 actually today. I use purple, red, black, blue, green, and like an orange or a yellow or something. If you're showing the color codes, totally pause, do that. And then really what we got to do first is we need to review or learn some trigonometry to really get how to do this stuff with vectors. And so trigonometry is honestly, it's actually the mathematical study of triangles and their side lengths and their angles. That's actually what trigonometry means. And so we're going to be doing a little bit more in depth today to kind of figure out how to use this trigonometry stuff to actually find values of vectors. Because maybe in the future, I have a cannonball actually that's like right here. Maybe I launch it kind of along this line, and I need you to figure out how far it's going to go or how long it's going to be in the air. So that's really kind of where we're working towards. So first off is I just want to go in and say here that like maybe there's some angle, and I'm just choosing this one. I could have chose the angle up here. Now this little symbol I'm using is theta. It's a Greek letter. It's Greek letter theta. And so really based, if I'm looking at this angle here, that means then that if I kind of went straight across from it, so the opposite side from it, well, this thing here is the opposite. Similarly, the side right next to it, the side along here, this is called the adjacent side. Adjacent just means next to. And then since this actually is a right triangle, that's a 90-degree right there, this is the hypotenuse. Okay, cool. Sorry, my ends and U's look the same. Now, a couple things from trigonometry, just in case you haven't learned it yet, or you maybe need a little bit of a refresher, is sine is what's called the opposite over the hypotenuse. And so we'll look at like what the heck that actually means in a second. But I'm just going to go over right here, and maybe I'll just say that sine is opposite over or divided by the hypotenuse. Now this is where some of our colors are going to come in handy. I'm actually going to do these ones in blue, just like that, something like that. Oops, wrong one. That guy, blue, perfect. Now, so sine is opposite over hypotenuse. So we have like SOH here. Now, cosine, so what that actually means is if, I don't know, if the side of this was 4 and this was 7, well, sine of this angle, so we'd write like sine, and you don't need to write this part, but sine of my little theta here would be opposite, so it would be 4 over 7, opposite over hypotenuse. So sine of this angle is opposite over hypotenuse. That's kind of how it works. Now, similarly, I'll start with green here for my cosine. Cosine is adjacent. It's adjacent over the hypotenuse. Okay, so that means that if I was doing cosine of my angle here, I would end up having, I don't know, maybe this, let's say this is 3. Well, then we would have adjacent over hypotenuse because cosine is adjacent divided by the hypotenuse. So I'd have 3 over 7 then. That's kind of how this would work, okay? Now, similarly, our last one here, I'll use orange for this, tangent. Tangent is just our opposite divided by our adjacent. I bet I fooled some of you on that one. So we have SOH, CAH, TOA. So we have SOHCAHTOA. That's the way I learned it earlier in school. I kind of built in a pretty absurd, silly way that maybe if it helps, great. If it doesn't help, sorry. But here's actually kind of our little ridiculous misnomer for it. So we're going to say that some, so we'll go right here, some old, and I would encourage you, make up your own with this. If you want to pause, kind of think of your own creative thing with SOHCAHTOA, I would encourage you, like, do something silly that will kind of like jibe with you. This is just the one that sticks with me. I don't know, go figure. I think it's kind of funny. So some old hippie caught another hippie. So we have SOH, so CAH, Toa, tripping on acid. Some old hippie caught another hippie tripping on acid. SOHCAHTOA. Like, please make up your own silly, absurd thing. This is just something that's going to help you tremendously, though. Like, whatever your silly thing is, the more absurd it is, the better it will stick, and the better, like, you'll remember it. And that's kind of how we like to do things. So with that, let's start using this to actually start analyzing the boat problem. So before I write anything, here's the gist. I got this boat. Okay, now I don't actually own a boat. It'd be kind of cool to own a boat. If any of you have a boat, I'd love to go out on a boat. So I have this boat. No matter which way I aim the boat, my boat goes 5 meters per second. Okay, my boat goes, if it's going upstream, like speed shows it on the boat, the speedometer says I'm going 5 meters per second. Downstream, it says 5 meters per second. If I go across over here, it still says 5 meters per second. Okay, and what I'm going to do originally is I'm going to aim my boat straight across. So I'm going straight across this way, and the speed, V boat, or VB, is 5.0 meters per second. No matter which way I aim the boat, it goes 5 meters per second. Now, there's a river, though. The river, you can probably see the river already here. The river always goes downstream at 3 meters per second, okay? So we can think about it and kind of just do a couple quick things here. If you were standing over here on the side like this, and I aimed the boat upstream, I'd have 5 meters per second going upstream. I'd have 3 meters per second going downstream. So overall, I'd be going upstream at 2 meters per second compared to you right here on the land. All right. Still, my boat's going to say I'm going 5 meters per second because I'm still moving at that pace, at least as far as my boat is concerned. That's what the speed reads on it. Now, if I kind of did the opposite, and instead, if I went downstream, well, my boat's going to put me down at 5 meters per second compared to the water. But the water's also going downstream at 3 meters per second. So I'd have kind of my 5 meters per second and my 3 meters per second. They really are going to just add together and give me a total velocity of 8 meters per second downstream, right? That's kind of our two extremes, straight up and straight down. Now, what we're looking at today are kind of some values in between, kind of some interesting, like unique problems, and we'll have to use this SOHCAHTOA stuff to do it. So here's the boat problem, really. And I'll get rid of myself over here, or you, or whoever that is. So we want to find out how fast and at what angle, at what angle must the boat move relative, and I'm going to use a fancy term here, relative to the horizontal. Now, really, all that means is a horizontal line straight across from left to right. So really, it's just a line straight across from left to right. So, for instance, if I drew a horizontal, like where my boat is, it would essentially be on my line here. So horizontal would just be, I could even take my ruler here and we could just like go, oh, well, here would be my horizontal. So essentially, I'm trying to figure out, our question here is, how fast and at what angle must the boat move? That's it. Now, in version 1, we're going to say the boat originally aims straight across. That's what we've already drawn. So the boat originally aims straight across. Whoa, I guess I can't write today. Okay, so we can kind of think about this now, and we've done some kind of vector adding. We saw that in our video earlier, or maybe we haven't watched that one yet, but you will. And so all I want to do is I want to kind of take the two vectors I really have over here, and I'm going to add them tip to tail. Now, I challenge you to do the other way compared to me, and you'll find out you get the same value in all honesty. But let's kind of go with it here. So we have the velocity or the speed of our boat, and it is actually a velocity because it not only has a side, but it has a direction as well. So we have VB is our 5.0. We have 2 sig figs, meters per second. And then we have the speed of the river. And I'm not really like measuring squares or doing anything here, but I just know that the boat's magnitude is larger than the river's. So we have the river, it goes 3 meters per second. Now, using our tip to tail method, we can see, oh, if we add these two together, really, I end up having some vector that goes like that. So more or less it's like that. So this is actually the boat's final kind of velocity vector. It's the direction that it goes. Now, I bet you can maybe see that it's going to be going faster than 5, or it should be going faster than 5. But we'll kind of figure out what that is. So we want to find out what the length of this is, and we want to find out what this angle is, okay? Now, the easiest thing we can do first, right off the bat, is, well, we know the horizontal component. We know the kind of portion going left to right in the x direction. We know the portion going vertically kind of in the y direction. So let's just use the Pythagorean theorem here, okay? Oh, it's not like letting me pick my color. Weird. Wonder why. Okay, well, oh, there, of course now it works. We'll use the Pythagorean theorem. So that whole thing was like a squared plus b squared equals c squared, where c squared is the hypotenuse of your right triangle. And we have a right triangle here because this is a 90 degrees right there. So what this tells me then is that, well, we have the speed of the boat squared plus the speed, oops, oh, it looks like it's still not letting me pick cool colors. Well, the speed of the river squared, and that equals our total velocity vector squared. Now, for me, I want to get just the velocity vector, right? So all I need to do really is take a square root of both sides. So I end up having this whole thing again right here, and we're just taking the square root of it. That will give us our velocity vector. That's it. So all I need to do is plug in. It's pretty simple. So I'll just go in, I'll write here that I have my square root of 5.0 meters per second squared plus 3.0 meters per second, and that also is squared. And so 5 squared and 3 is 25, and then 3 squared is 29. So this actually is really our velocity. And now if I simplify that, I end up just having the square root of 25 meters squared over second squared plus 9.0 meters squared over second squared is our velocity, and 5 plus 9, that's 30, or 25 plus 9 is 34, so I end up having the square root of 34. So whatever the heck that is, the square root of 34 meters per second, and they're both squared, is my velocity. Now I have a calculator right here. I've already done it. This gives me 5.8 meters per second is how quickly the boat is going. So poof, we already know what kind of our magnitude is. Hopefully that made sense how we did it. Pretty straightforward, I think, once you get the idea on how to do it. So looking at our picture now a little bit more, sure, the boat is going to be jamming along this way in the direction of the black horizontally, but every little bit that it goes, the river is going to push it downstream. So in the end, it's going to have kind of some vector like this, in all honesty, and that's what we're really looking for. We have this vector, it's going at some angle, and now we know V. Now that we need to just figure out what the heck is that angle. So again, we have all this SOHCAHTOA stuff, And funny enough, we now know all of these values. We know v, we know the speed of the boat, we know the speed of the river. We could use sine or cosine, or we could use tangent. Now, because we already were given the opposite thing from our angle over there, right? And we have the adjacent, I'm just going to use tangent. So I just choose that one. You can absolutely use, you can use cosine, you can use sine. They both will give you the same answer. Actually, I would challenge you to use a different method than me here and make sure you get the same thing. So I'll use tangent though. So tangent of our angle is equal to, and tangent is opposite over adjacent. So now we just have the speed of the river over the speed of the boat. And now, here's the weird thing. I need to not have tangent of this angle. I need to have the angle itself. So we need to get rid of tangent on this left side, in all honesty. Now, maybe you're already a pro with this, and that's cool. You can just skip ahead. If you're not a pro, there's the thing that's called an inverse trigonometric function. All it is it's like the opposite. It's like if you're doing 3 divided by 2, well, it's like multiplying by 2 because it's the opposite of dividing by 2. In this case, it's the opposite of tangent. And ironically enough, it's literally called the inverse tangent function. So we'll take the tan inverse, that's what that little -1 kind of power right here means, of both sides. So we'll do the inverse tangent of this angle. That's really what we're doing. And then we're going to do the inverse tangent of, well, now we have VR over VB. We have the boat over, or the river over the boat. So we have 3.0 meters per second divided by 5.0 meters per second. And really it's kind of this whole thing here. So I can look and see that, oh, well, tangent and inverse tangent, those kill each other off. So really I do have just my angle alone right there. And I just have to poke this into my calculator. Now, if you have a TI-31, I can tell you that if you hit the second key up in the top left corner, it's a little light colored key, and then you hit the tan button, that's for tangent. If you hit the second key, it will make it do the inverse tangent instead. If you're using a different method, you need to make sure that you're getting the right value, because when I poke this into my calculator, I get 31 degrees. And so that is our answer for it, actually. It is 31 degrees, and I would say that it is below the horizontal, because our horizontal is this thing, and it's below the horizontal. So that's it. That's how we kind of do it. And just kind of as a note, we could have used sine of theta, and we would have used inverse sine, or cosine of our angle, and we would have used inverse cosine instead. So for instance, if I had chosen to use sine, well, I would have said that sine of my angle is equal to, and it's then opposite over hypotenuse, because that's the so right here in SOHCAHTOA in that thing. So what that would tell me to do then is I would just say 3.0. Whoa, that was kind of weird. I don't know what that is. Sorry. So 3.0 meters per second over, well, my big velocity, which we found is this 5.8. And then you would have had to use inverse sine instead of inverse tangent, and you actually will get the same exact thing, which is pretty freaking awesome. So hopefully my sine or cosine folks got that. Now, version 2, let's say the boat aims upstream so that it actually does go straight across. So that's what the whole goal is now. So really, we're saying that my boat instead aims at, I don't know how high up it really needs to go, but it's going to go this way, let's say. And we still have that the speed of the boat is 5.0 meters per second, and the river still goes downstream. So we still have the river goes downstream at this kind of V river, speed of the river, velocity of the river at 3.0 meters per second. So, but I'm saying that it actually does go straight across. So what this really means then is we're kind of doing this tip to tail thing. We're actually kind of adding these vectors together. We're seeing here that, well, v boat plus v river, that's this right here. This is my kind of speed velocity of my river, ends up causing it to go straight across. And so I'll use green again if it lets me. It seems like it's not liking that. And so that's what I'm trying to find now. How quickly is it going to go? We're still trying to find the same two things. How quickly will it go, and what does the angle need to be? Now, in the last one, we saw that it went 5.8 total when the boat only goes 5. So aiming straight across, its total effect was it sped the boat up. Now, if we're aiming upstream, though, like we are here, we're kind of partially fighting against the river. So in the end, I would guess it's going to be something smaller than this original 5. And hopefully that's kind of what we'll get. So I like to go over and draw the vectors again. So here is the speed of my boat. So v boat, our 5.0 meters per second. Here is our velocity vector for our river. That's our 3.0 meters per second. And we're trying to figure out, like, what is going to be this total velocity for it, and then what's that angle. All right. So again, we oddly enough kind of have two of our three sides. Hopefully that kind of triggers in your head, oh, maybe we can use this Pythagorean theorem thing again. So we're just going to use this a squared plus b squared is c squared. But now we know c squared, and we don't know one of the other sides. When before we knew really our a squared and our b squared, and we were finding c. Now we're trying to find one that isn't c. So use Pythagorean again. And so here I have that our velocity, let's use our total velocity plus our river's velocity squared equals the boat's velocity squared. And the reason I know that is the hypotenuse is always the biggest side, and that's always the one that's going to be alone. It's also always opposite of this 90-degree thing right here that I have, okay? So just kind of cueing you in on that if you're someone that didn't know that one. So now, if we're trying to find how quickly the boat's going, that's v. I need to get the v alone right here. So I'll do a little algebraic step. I'll subtract this VR squared from both sides. And so I'll end up having, I can talk, is we have our velocity squared is equal to the velocity of the boat squared minus the velocity of the river squared. And if I want to get just the velocity of the boat at the end, the total velocity, this part in green alone, I need to square root both sides. So I'll go over, and if I square root this side, well, that gets rid of the square right there. Beautiful. So now we just need to plug in our values for it, which is pretty neat. So all I'll do is we have our velocity at the end is equal to the square root of, and we know now that we're going to be squaring 5 and squaring 3. So I'm just going to skip a step and say we have 25.0 meters squared over second squared minus 9, and let's use blue so we know that that's our river, meters squared over second squared. And we're taking a square root of all that. And so, well, now we have 25 minus 9, that's 16. So the square root of 16 meters squared over second squared, well, that's just 4. 4.0, we're keeping sig figs, meters per second. So that's actually how fast the boat will be going straight across the river if it aims up like that. And so just like I kind of guessed, and hopefully you kind of intuitively agree with, it's actually going a little bit slower than the 5.0 meters per second that the boat goes at, kind of as far as its speedometer reads. So now let's find the angle for it. Well, now we know that this thing is 4.0 meters per second. We have all three sides. We could use sine, we could use cosine, we could use tangent. I'll just mix it up just kind of for funs here. And so let's use sine this time. So sine is going to have us use the opposite over the hypotenuse. Now, we didn't even need to use or know what the green vector was then. We could have done the Pythagorean theorem second. And so if that didn't make sense, I'll kind of show this. So that means then we can use sine of our angle is equal to, and we have the speed of the river over the speed of the boat. And so again, we're going to have to use this inverse cosine thing, and I'm just going to write this a little differently to kind of mix it up. Maybe one of these makes a little more sense to you. So I'd say then that sine of our angle is equal to 3.0 meters per second over, that's the speed of the river, over the 5.0 meters per second that the boat itself always travels at. So again, to get rid of the sine here, I need to use inverse sine. And so it's just like this step above where we had to kind of do inverse tangent on both sides. We're going to use inverse sine on both sides. So if I use inverse sine on both sides, well, I'll have the inverse sine of sine of this angle is equal to inverse sine of my 3.0 meters per second over my 5.0 meters per second. And so in the end, we see that inverse sine of sine, those kind of kill each other off. And so we just have to poke into our calculator, really, the inverse sine of this 3.0 divided by 5.0. And that gives me, if I did this correctly, 37 degrees. And so that tells me that actually our boat had to be angled from the horizontal. So if our horizontal is kind of like this line across, it had to be angled up there 37 degrees is what actually had to happen to result in the boat going directly across the river, just perfectly so. Now, I want to backstep and say that right here, we could have done all this Pythagorean stuff second. Everything right here in the yellow, we knew when we first were given the problem. We knew the speed of the boat, we knew the speed of the river, and so we could have just used sine first. We could have done the yellow part first, and then the Pythagorean theorem part second. So these two are kind of totally independent of each other because we used sine. If I wanted to use tangent again, well, then I would need the opposite and I would need the adjacent, and then you'd have to get this guy first to kind of use it. So you can kind of be creative with the order that you want to do these things. So our last version here. Now the boat aims downstream, and this time I'm giving you actually the angle. So the boat aims downstream at 25 degrees below the horizontal. Okay, so this is where it starts to get maybe a little bit weird, okay? Because the idea is, well, we obviously still have our river. The river hasn't changed. So the speed of our river is the same. We still have our velocity of the river is downstream at 3.0 meters per second. And now our boat is already going to be aimed at 25 degrees below the horizontal. So I'm even just going to do a little horizontal right here, just so we kind of have that clear and obvious. And so my boat's going to aim down like right about, I don't know, let's say there. Okay. And this will be my V boat. Okay. So we have that. Now, here's where and why it gets a little weird, because isn't the river going to make it go even farther downstream? Because now this has kind of a part of it. We kind of think of like this black vector now. It actually has like a part in the y direction and a part in the x direction. And so really, if we kind of add our velocity of our boat to this river vector, well, in the end, our boat's going to be going at some different angle down here, because the river's gonna add to the boat's speed and its velocity, and it's kind of gonna change that. So really, we know then this angle in black is 25 degrees. We know that one, okay? And we know really that the river is gonna be the thing that kind of makes it speed up more. So this really is kind of the river's vector itself. So actually, maybe I should move that a little bit over or could just maybe get rid of this green one and make it a little bit bigger, in all honesty. So it's just easier to see. So we'll copy that guy. We'll bring it down here. And now we can kind of have a nice, cleaner, bigger picture of this all. And so we'll go and write, oops, what was that? Right there. So now we're trying to figure out what is the total angle. So we still want to find out what the angle is. It's this total thing from the horizontal, that's theta, and we want to figure out how fast the boat's actually going. So we have to do a couple things here. And so the first thing we want to do is we want to kind of break up just the boat's part. And what I mean by that is the boat has, in this black vector, the boat has a part that's going down to here. It has kind of this velocity of the boat in the y direction. It's just the part of this black vector that's in the vertical direction. So I'm going to call this VBY because it's the y part of the boat. And then I'm going to go over here and maybe I'll use purple. And now we'll go over here and say that, well, really right here, we actually have the velocity of the boat in the x direction. And so here's why we care and kind of where I'm going with this. Well, is if we can figure out this part right here, couldn't we just add the y part of the boat's velocity to the river because the river is going in just the y direction is really what I'm kind of getting at. So then if we could get just both of these y parts and we know that, then we ultimately know this giant, and I'll use yellow, we know this giant yellow side of it. And then if we know the purple as well, kind of right here, now I'm just drawing all over this, well, then we know two of the three sides of this wombo triangle then, okay? And if we know two of the three sides, we can just bust out our Pythagorean theorem again. So if you lost me on that, or if I lost you on that, or something was kind of weird on that, because my computer just got a little weird, I'm going to go over this a little bit more. So first, really what I'm saying is we need to find the x and y components of the boat's velocity because we know the boat's going at a 25. So if I want to just find VBX and VBY, well, I know the boat is always going at this 5.0 meters per second, and I know the angle. So I can actually go through and start finding these values. So I'm going to use sine because sine is opposite, and so opposite my angle in black would be VBY. So looking at us here then, I would say that sine of 25 is equal to VBY over VB. Really, I'm looking at this triangle and I'm saying that, well, the opposite is right there and saying it's opposite over hypotenuse. And so I just said sine is, well, opposite over hypotenuse. This thing over that thing. That's all it is. Okay, cool. So now let's actually do something with it because we know how fast the boat goes. It always goes at 5 meters per second. So if I were to go over and multiply both sides by VB, well, it would cancel on this side and then I have a VB over here, right? So that's all we're going to do. We're just going to rewrite it that way. And so in our next step, I have that VB times sine of 25 equals the y part of the boat's velocity in the beginning. And so I can plug in my 5 then, 5 meters per second times sine of 25. I poke that into my calculator and I get 2.1 meters per second. That is the y part of the boat's velocity. Now, we're going to come back to this. We're going to use this in a little bit. I like to just kind of oval the things that will come in handy later, but aren't like a final answer. So I'm not going to box it. Now, if I used sine to find VBY, well, I need to use cosine then to find VBX because that is the thing that is adjacent to this 25-degree angle. So we'll do almost the same exact thing, but with cosine now. So cosine of 25 is, well, the x part of the boat's velocity over the boat's velocity. So I'm going to skip a step here. We know that we can take this, multiply it over there. That's really what we did just before. And so I would have them at 5.0 meters per second times cosine of 25. Well, that ends up equaling 4 0.5 meters per second. That is my VBX. And so that's another handy one we'll use. I'm going to circle it. Cool. Awesome. So now, what the heck did we even just do? Why do we care? So again, we care because there's actually a bunch of triangles here, right? Well, we have the triangle that's the black and the red and the purple. That's a triangle. We have this other wonky triangle that's not a nice easy triangle. That's the black and the blue and the green. That triangle kind of sucks. But then we have a bigger giant triangle that's the outside. That's purple and blue and red and then green. And so the whole idea is if we can find this guy, and if we can find what these two add to, well, we know the two sides of this big giant right triangle, and we could use Pythagorean theorem and get our velocity kind of at the end, is what this is really kind of saying and what we're getting at. So now what I can do is just throw down our Pythagorean theorem and we're good to go. So use Pythagorean. So we end up having really here that our v squared equals, and I'll kind of zoom out so we can see the picture again a little bit, equals, well, it equals the x velocities, and there's only actually one x velocity. It's just this vbx. That's all it really is here. So I'm just going to say vx squared plus vy squared, where this x is all the x velocities and this y is all of the y velocities. And so here's exactly what I mean. Rewriting this again, we have that our total velocity squared is equal to, well, in the case of our x velocities, the only x we have is at 4.5. So we have 4.5 meters per second squared plus, because again, we're looking at this giant yellow triangle again, right? We have the x's, we have the y part, so we have the horizontal and then the vertical and then the total. And so to find my total y, though, I need to add the red and the blue. So we have the red is 2.1, the blue is 3. Well, 2.1 plus 3, that's 5.1. So that ends up giving us a 5. Oops, let's not use yellow. Or maybe we're stuck with yellow. 5.1 meters per second, and we're using Pythagorean theorem, so it's squared in the end. So this ends up becoming, and I am kind of mixing up my algebra steps, so you can see that there are multiple ways to do it correctly. I end up having here a, what did I get? It's, I think, 46, and then some change. But since we're just going to keep it to suit 2 sig figs, we will just leave it at that. So I'll have 46 meters per second. And this is squared though. So really to get just my velocity alone, I take a square root on both sides. And this one, where did my calculator just go? So we'll do our square root. Where is my calculator? I can maybe do this one in my head. Okay, no, I found it. 46, the square root of that is 6.8. 6.8 meters per second. So we now know the speed of the boat when it aims downstream and the river kind of helps it. And so this 6.8 is bigger than the boat's original 5. That kind of makes sense. The river is kind of pushing the boat along and speeding it up. So the last step, we need to find our angle. So now find our angle from the horizontal, really. That's kind of what this means. The total angle from the horizontal. Okay, now, really, you can use sine, you could use cosine, you could use tangent. I'm just going to use tangent. So let's use tangent. All three work though. All right, just throwing that out there. So really, I have tangent of this big old giant angle. This angle's from the horizontal all the way over here, right? Well, that's equal to all of my y's or all my opposites over all of my adjacents. So tangent is again opposite over adjacent. So what that really tells us then is tangent of this angle is equal to, well, the opposite of this giant angle, well, it's this entire vertical side. So I have my VBY and the rivers. So I have the Y part, the vertical part of the boat's velocity and the rivers. So I have this 2.1 plus the river's 3.0, and so I end up having 5.1 meters per second over the adjacent. And the adjacent really is just this x part of the boat's velocity, which we found to be 4.5 meters per second. Now, the neat thing you'll find here is that since we're dividing meters per second by meters per second, they cancel. And that should hopefully check out. If we're finding an angle, we shouldn't have meters per second for like our units. And just like our earlier part above, where we did version 1 of this, since we're using tangent again, we'll end up having to use the inverse tangent. So I am going to skip a step. If you want to write like the whole like times inverse tangent by tangent, that's fine. But this ends up being that we have our angle is equal to, well, the inverse tangent of 5.1 over 4.5, because our units canceled, and that ends up giving me 49 degrees. Wowzers. So this one was quite a bit more work doing this version because we had all these crazy triangles going on in here, and we had to break things down to get the total side length here and the total side length here, so we could then use Pythagorean and get the final kind of velocity. And then with those, we could use sine or cosine or tangent. So that's it. I hope that makes sense. I'll see you next class.